Hello, everybody. Can you hear me? How are you guys doing? All right. Good, good, good. Just wanted to make sure. Um, we're going to get started. Sorry, I was dealing with a couple of students from um, my last class. Um, Question. Did anybody have any questions? I'm going to put the thing up, but everybody was clear on what was it? What they're doing for the lab practicum. I'm going to put the stuff up, but I just wanted to make sure everybody was clear on that because apparently there has been some type of confusion. I'm pretty sure it wasn't you guys, but I just wanted to make sure whether or not you guys was clear on what you guys was doing for your lab practicum. It's basically just writing a paper because I think some other students were unclear. And I think it just been my other class. I just didn't know where it came from, that they had some questions about the lab practicum or doing the lab practicum. And I just wanted to make sure you guys were cool with just doing your paper for the lab practicum and everything. Yes, no, give me some feedback.
Yes, ma'am.
Okay, all right. How about everybody else? You guys are good on that too?
Yes, ma'am.
Okay, all right. I just wanted to make sure because I know I just didn't know where it came from, but they had some questions about the lab practicum, and some people higher ups brought it to my attention, and I was just trying to like make sure that we can't do a physical lab practicum because we're not in the lab. So the next best thing to do was just write papers on it, which you guys were doing anyway. The only difference was that I know most of you guys wanted to actually demo parts of what you were doing for your lab demo anyway. And that was the only difference is that you just can't demo it because we're not in the lab. So I just wanted to make sure um, that was cleared up. Um, let's jump back into this. How far did we get yesterday on our slides? Because I wanted to make sure that we finish up this particular chapter. So,
We
Sydney,
stopped at the addition of organometallics to aldehydes and ketones. That was the last slide that we did.
okay, 50. Okay. All right. I just wanted to make sure I knew I was somewhere in that area. I just didn't know exactly where. Thank you so very much, Sydney, for that.
You're welcome.
All right, let's get started. We're going to finish up um, this chapter today. Um, I'm trying to see if I'm going to start chapter 18 because the next test is going to be 17, 18, and possibly 23. I think it's 23 or 24. That's that. And then, like I said, chapters 19, 20, 21, and I think 22 that deal with all the carbonyl chemistry. With those chapters, I'm gonna probably go ahead and just pre-record those so that you can have those because that information has to be on the test as well. So I'm gonna probably pre-record those particular chapters. So I'm gonna probably try to get started on those. If we have time, I will lecture on those, and I'm pretty sure we will. But I want to leave enough time to actually go through and go over and review what you need for the final exam. Um, Because of everything that's going on and with the final exam, I'm gonna probably have to do it in two parts. And that's just because normally when we give the exam online, um, I think we're limited to the number of questions we can put on the exams. I think it stops at 50. So I may have to break it up into two parts. And so that's what I'm going to try to see and work out. So it'll probably be a two-part exam that you will have to do. And because I want to keep it as close to what you're going to take as possible. And usually those exams have about 70 questions on there. And so since we limit it at 50, and one of the things I do, and will try to talk to Dr. Craig, I probably want to do a few more, only because I want to be able to help you guys out. So I don't know if you want me to keep it just at the 70 questions or if I could go to 100 questions, because the more questions you have, the less you miss for that amount. And so instead of they're counting, 1 point something a piece, it's just 1 point per each question, and then you given a little bit more leg room. So I want to talk to him about that. So I need to run that by him, but that's my plan, is trying to put it into two parts, um, so that you can get the same amount of questions, if not a few more, to actually help you out for the exam. So that's something I need to talk to him about. Because I'm going to get started making your final exams probably within the next week. And so it's just going to take a little time and a little bit more crafting of the exams. Like I said, I wasn't able to look at the exams, but he told me what topics are going to be that was covered on the exam. And so I'm going to have to look at questions and stuff that we have had before to kind of give you an idea of what's going to be on the exam. And so I'll be able to do that. And I want to be able to do a review with you guys on what's going to be covered on the exam. So let me talk to him about that. But I will give you some hints on what's going to be on the exam and everything. And I got a list right here what he gave me. So I want to do that. So I want to make sure I cover everything so that it can be on there for you guys. Okay, let's get started. I'm going to cut my camera off, and then let's get started with this. Can everybody see my screen? At least I hope you guys can. I think it's showing. Okay. All right. So where I left off at is here. And let me open this up real quick. Okay. And what you have here is basically um, your addition of your organometallics to aldehydes and ketones. Now, when you treat these with bring your reagents and you follow it up with water, you would get an alcohol with a new carbon-carbon bond. And so with this reaction is an addition because the elements R and H are added across the pi bond. So when you do it and you react the aldehyde or ketone, you're going to get an alcohol. Now, to what degree of alcohol you get, it just depends, but you will get an alcohol. Now, you can have nucleophilic addition of the Grignard reagents. Now, as I said before, and I tell you now, a lot of times, my mentor, I have several mentors who are either organic chemists or they're material scientists like I am, but their background is chemistry mainly. And this is mostly what they use in their lab with their research. They use Grignard reagents, and this is just one of the things that When they do this, this is one of the things they have on hand. And they do a lot of these in the lab all the time. Now, when you talk about this reaction, this is just a general reaction for nucleophilic addition. The nucleophilic attack by carbocation followed by protonation. This is generally what they do. Here, when you look at this mechanism, it's shown using R m sub x, and that's up there. They put 20.6, it's supposed to be 17.6. But the same steps occur with um, different reagents that have lithium in it and the acetylide ions. So, and that's because anything, lithium itself, even though it is one of the smallest elements, is also the most reactive element. And so with that, you're gonna see this happen a lot, especially with lithium. And so it will react fast. So anything that is mixed with lithium or have part of lithium in there, it will create a very fast reaction most of the time. And so what you see here is when you do the organometallic addition, let's just say you got formaldehyde, and you guys are familiar with formaldehyde. Um, and then you mix it with something and you do this addition, and then you add water, you will get a 1 degree alcohol. And I mean, this is something that we can do even in the lab at school in working with formaldehyde. That will happen. Now, if you just have other types of aldehydes that where your R group is not the same as your hydrogen group, you'll get a 2nd degree alcohol. Now, and that's basically when you have a ketone, the same thing will happen. Um, it'll form a 3rd degree alcohol. So it just depends what you have. So if it's formaldehyde, you will get a 1 degree. Other aldehydes, you get a 2nd degree. And then if you have ketones, you get 3rd degree. And so that's what it is. You can go from alcohols to aldehydes and ketones, and you can go from ketones and go back to alcohols. So these reactions, depending on which way it goes, can work in reverse. It's just what you use in the process as your reagent. Now, alcohols formed by the organometallic addition. You use this reaction to pair 1 degree, 2 degrees, and 3 degrees. So that's what they use. In this case here, they used um, methyl. So they got methyl on there with magnesium, and then they formed that 1 degree alcohol. For the benzaldehyde, what they did is basically the lithium aluminum sulfate of a hydrate, so something with lithium in it. So they just got lithium over water. They got a 2nd degree alcohol, and then the cyclohexanol, they got something else with lithium in it again, and reacted over water, and they got a 3rd degree alcohol. So it doesn't matter. So what they mostly doing is with formaldehyde, you don't have to have um, that much reactivity to get a 1 degree alcohol. They just put something really simple on there with the magnesium and methyl group. But with the other ones, they are reacting them with a lithium component in there. And like I said, anything with lithium in it would make it highly reactive. And so this is one thing that they looked at. And what is this? This is, I think, a version of a steroid. I haven't really looked at this one. So like I said, even with this one, it's more complex structure, but they did the same thing. They just reacted it with a lithium group, and that's how they got it. And basically, They reacted, and then in one step, and this is basically what they came up with. Now, what they did was it was RO. Then when they reacted it, it was RO, and then they did one more step, and this R group kind of went away, and then that was replaced with hydrogen. Now, the C18 juvenile hormone help regulate complex life cycles of insects. And so this is one of the things that they do um, in a lot of different labs. And so they do the same thing. They react that same thing to a ketone and it give it an alkyl oxide, alk oxide, which is pronated from water to form that third degree alcohol. Now you got an ester group on there. It can react with the Grignard reagent. It's less reactive than the ketone carbonyl. So this control of the reaction, and you got nucleophilic addition going on, and that select what type of ketone that you have. So what they do is once you do that, you can form this in one step. Conversion of this to epoxide, you we discussed that in chapter 9, and so you can have this that forms as well. So juvenile hormones um, maintain the juvenile stage of an insect until it is ready for adulthood. Um, so why do we care about that? So they use that to control the insect population. So the application of this synthetic hormones to eggs or larvae prevents uh, maturation. And basically what they're doing is it's a preventative. So insecticides and all of that, that's why they use this for. Methoprene is used in cattle salt blocks to control horseflies and on dogs and cats to control fleas. So this is basically what you get. It's juvenile hormone. That's what they put on there, flea and tick control. And so that's what it does. It controls the flies. So like if your animal has a wound or something, and usually sometimes when animals have wounds, they're not dead, but they have a wound and that wound is open. A lot of times flies like to fly up to that wound. And that's what they do. They like to prevent that. And then like if dogs, and I know that, for example, my little Snooky, she's allergic to fleas, and so she'll scratch until she literally bites herself. And then when she does that, she breaks her skin. And then if she breaks her skin, that's when the flies want to come around, and then they can cause infection too. And so that's what they put in there. So they put in flea and tick control. So that's one of the things that they put in there. Now, can you take bring your products and analyze them? And when you look at this, you can look at carbonyl chemistry, and that's what I said. I want to group the carbonyl chemistry kind of separately. Like I said, this chapter touches on all of the chapters really after this up until chapter 24. But what I wanted to do was really put those in a separate category because carbonyl chemistry is just one of N by itself. But you do use Grignard reagents in that. Which one determine what carbonyl and Grignard component are needed to prepare a given compound. This is what you have to do. You got to find the carbon that's bonded to the OH group in the product. And then you got to break the molecules into two components. One alkyl group that is bonded to the carbon with the OH comes from the organometallic reagent. The rest of the molecules can come from the carbonyl component. So you got to break them up into that. So that's what you have to do. And so you can do synthetic analysis of your Grignard products. Um, why is that important? If you're trying to get somewhere, especially when you're developing not only a new chemical process, but a new chemical in itself or a new drug, and you're using the Grignard reagents. This is just one of the ways that we use to check them to make sure that they are viable to be used. And so that's why sometimes you see this retrosynthetic analysis. They use that to make sure it's the proper one to use. Um, because sometimes, and you know, when you look at these Grenier products, they are selective too. And so this is one of the things that they use. Um, and then this is how you determine, how do we determine this? And you got to make sure that you're using the proper one for the proper application. So let's look at 3-pentanol. And so you have a 3-carbon aldehyde. So what they did was basically um, went to the 3-carbon aldehyde. You get the penthreonol, and then this is formed from the bond by the Grignard addition. And then so you got uh, magnesium bromide, and then it's a 2-carbon Grignard reagent that's there that has the magnesium bromide on the end. And so this is the way that you can do those analysis and look at, okay, what is that on that back end? And then let's take a look at that. So we done broke part of it up that goes to the carbonyl group, but we want to see what is also hooked on to that hydroxy group to see how we break it up and how we analyze it. And so that's what they do. Now, writing the reaction in the synthetic direction that's from the starting material show whether the synthesis is feasible and the analysis is correct. Now, with this, one of the things that even I've seen with working with these in the lab, there are more than one way to synthesize these. And a lot of time, it's pretty much what you're looking at is, can we do this? Are we able to do it? And which way would be feasible to do it? That's the main question. Now, when it comes to this, there are limitations. Now, when is that you can't use them when it got both a carbonyl group or that contain both the carbonyl group and you got an NH bond or a H bond. So the carbonyl compounds that also contain your nitrogen hydrogen bond or your OH bond, they undergo an acid base reaction. They do not undergo nucleophilic addition. It's just going to be a simple acid base reaction that they're going to undergo. And so that's what happens in cases like this. So there are limits to using organometallic reagents. Now, sometimes what they do is they use what we call these protecting groups. So when they do that, they use this strategy. They convert the OH group into another functional group that doesn't interfere with the reaction. So it's a protecting group. So basically what you're trying to do is you want to put it in another functional group that basically remains inert, just like an inert gas. That's what you do. Then once you do that, you carry out the reaction, and then you go back and remove that protection group, and that's called deprotection. A common OH group protecting group is a silver ether, and so they do that in order to react it. So sometimes you have to do a series of reactions, protect this part of it right here, carry out your reaction, and then remove it. Why do they do this? Why do we care about this? Think about it even in medicine, and I know a lot of you guys are trying to go to medical school and different things. Think about it like this. If you are trying to create or synthesize a new drug, and you hear this all of the time about drugs having all of these side effects, what you want to do is, especially with the OH group, we're made up of water. And you know, lights dissolve lights. That's the one thing that we as chemists, we say that all the time. Lights dissolve lights. So if you got that OH group on there, you know that it's something attached to it. Just like I was just talking to my students about alcohol and how ethyl alcohol goes into your system and everything. You want to convert that OH group so that whatever that you're working with goes and attack what it needs to attack. And sometimes medicines work like that, that you have to set up mechanisms to whereas um, it dissolves in the body, but it has to go to where it needs to go to attach itself to either remove something for your body or transfer it or translate it into something that it can go out. So sometimes you have to convert that OH group because it can probably just dissolve into the body and make some adverse reaction. And so that's why they do that, because sometimes we're working with stuff, especially if it's something that's water soluble or anything like that, you want to protect that group and then redo it in water. So that's one of the things that you have to look at. So what they're looking at here is hydroxyquinone. The OH proton in it is replaced with a protecting group, and they call that PG. Because the product is no longer has an OH proton, it can undergo that nucleophilic addition. And in step two, um, they add this, what is that? That's CH3MgCl. So you got methyl, you got manganese and chloride, and you add it to that carbonyl group. It yields a 3-degree alcohol after protonation with water. And then when you remove that group, it forms the desired product. So you have to protect it because what's going to happen is you're just going to have the alcohol maybe form faster, or what it is just going to dissolve. And then you lose actually getting the alcohol itself. And so that's what it did. The carbonyl group yield that 3-degree alcohol after the protonation with water. And then removing of the protecting group forms that product. So terbutyl dimethylsilyl ethers are prepared from alcohols by the reaction with terbutyl dimethylsilyl chloride and an amine base, usually imidazole. And so they use that a lot. Um, so the silyl ether is typically removed with a fluoride salt. So they'll use tetrabutyl ammonium fluoride to remove it. And then, like I said, they'll generate that alcohol. And then that's what happens. You can keep on doing that and regenerate that. So if you want to prepare other ethers. So they use this as a protecting group to make the synthesis of 4-methyl-1,4-pentadiol by a 3-step reaction. And so that's what they're doing here, and they show how it goes through all of this to get that. Okay. Now, what about other things? Now, you can have these other organometallic reagents, they can react with the carboxylic acid derivatives, and they can form two different products. So that's what can happen. Um, and that depends on the identity of both the leaving group and the reagent. Now, with these reactions, you can carry them out with esters and acid chlorides. They can form ketones or 3 degrees alcohol. And so, what I'm saying here is if you got anything that got lithium in it or the magnesium in it with the chloride in it, the acid chlorides, they will react. So, reactivity makes a difference in the selective reaction. Um, so that's what it is. We talked about that in you saw that in General Chem or Foundational Chemistry 1 when you talk about that. And this is important because these reactions can really determine what type of products that you get. Either you get a ketone or you get an alcohol. So it just depends. So you have to look at which reagents you use with what. And normally, a lot of time, like I said, a lot of my mentors that are um, organic chemists, they have all of these on hand because they don't know which one would pair best, and they have to just try all of them to see which one will react best. And so, a lot of times, they have a lot of these reagents on hand. Now, both esters and acid chloride form 3 degree alcohols when they are treated with two equivalents of either Grignard or organolithium reagents. So it doesn't matter, but ester and acid chlorides will form 3 degree alcohols. Um, and it has to be treated with two equivalents of either the Grignard or the organolithium reagent. So doesn't matter with those two, they will form the alcohols. It's just the amount of the reagents that you're using. So in this case, concentration is important. And this here just shows you um, basically the reaction. And it goes through the same thing. You got your nucleophilic attack, that pi bond is reformed, and then that leaving group leaves, it formed that ketone. And then it attacks again. And so you got a nucleophilic attack, it formed that alkyl oxide with no leaving group. And then when it protonates, it forms that 3 degree alcohol. So it goes still go through that nucleophilic attack. So it's still going through that. And it's going to form that alcohol. So it's just the amount that you use. Now, there are other ones that are out there that can be used. And those are called organocuprate. And so those are the ones that have um, the copper in them. Now, what happens with the acid chlorides, um, acid chlorides normally have the best leaving groups because of that chlorine ion. Um, it'll react and give a ketone as a product. Esters, on the other hand, have a poor leaving group. They're not going to react as much. So that what goes on there. Now, now you can have Grignard's reagents that react with carbon dioxide, and they give you carboxylic acids after protonation with um, a water-based acid or aqueous acid. So this is called carboxylation. So the carboxylic acid form has one more carbon atom than the Grignard reagent when it's prepared. So you can react it with carbon dioxide and do that as well. And I have done that in the lab several times, and I did that in my polymer chemistry class. And I have done that in organic chemistry because, like I said, I have my mentors. They are all about working with green reagents. That's their deal. That's their thing. Now, um, a lot of them and a lot of my work have really dealt with epoxies, making different types of epoxies, making the epoxies a lot stronger. Um, Organometallics, what they do is they open those epoxy rings to form alcohol. And so that's one of the things that, um, like I said, a lot of my mentors really looked at. And so you can use those reagents to open those epoxide rings. And so um, they're strong nucleophiles that can do that. Now, it's the same two-step process with other negative charge. It's attacked from the backside of the epoxide, then it's protonated, and that's what happened. Now, when it's unsymmetrical, the nucleophilic attack occurs at the carbon that is less substituted. That is what happens. So that's the thing that you have to look at. So sometimes you have that backside attack. So that is what happened with these. So if you got something that's unsymmetrical, it's going to attack at the one that is less substituted. So what about if you got alpha and beta unsaturated carbonyl compounds? What happens with those? They are conjugated molecules. They got a carbonyl group and a carbon double bond separated by a single um, sigma bond. So resonance shows that the carbonyl carbon and the beta carbon, they don't have a positive charge, partial positive charge. And so with that, you can get different resonance structures, and then you're going to get hybrid sites, hybrid that has two electrophilic sites on there. Now, what does that mean? That basically means they can react at two different sites. So it can do a 1,2 addition or it can do a 1,4 addition. That's what can happen. And you get a alytic alcohol, or you can get a carbonyl compound with the new substituent on that beta carbon. So if you have that, it can react at two different sites, and you can have still that addition, but you can get a 1,2 or a 1,4. Now, the 1,2 mechanism, they're exactly the same as those for the nucleophilic addition of the aldehyde or ketone, and that is followed by protonation. So you have that, it is still the same thing. And what I want you guys to get, you're going to have that nucleophilic attack, you're going to have protonation. That is what's going to happen. That is what you're going to see. The 1,4 addition, you have still that nucleophilic attack. You have the protonation on the carbon end, and then you have protonation of the oxygen, and then you get that enol. That's what happened, and it's a two-step process. So same 1,4 addition product that results from protonation on the carbon. So you can have 1,2, 1,4. Now, what's the difference between the two? What happens? Organolithium and green reagents, they're gonna give you the 1,2 addition products, and because of the organo cuprate, because it's less reactive, it's gonna give you the 1,4 addition product. So that's the difference between 1,2 and 1,4. 1,2 comes from the organolithium and the green reagent. Because the 1,4, the organocuprate, is less reactive. So let's take a look at these, summarize these up. Let's finish up this particular chapter. Your organometallic reactions. Um, RM, they attack the electrophilic atoms, especially the carbonyl carbon. That is what happens. So organometallics, you've got your carbonyl groups, it attacks the carbon dioxide, it attacks the epoxide. After an organometallic reaction adds to that carbonyl group, the fate of the intermediate depends on the presence or the absence of a leaving group. Then the polarity of the RM group determines the reactivity of the reagent. All right, so synthesis. Now, we talked about oxidation and reduction. These reactions, we spent a whole chapter on this. So when it comes to oxidation and reduction, this is very important because the conversion of a functional group to a good leaving group, it allows for other reactions. So when you talk about synthesis, you really, oxidation and reduction is so important. And like I have told you guys before, um, when I looked at older books and when I took organic chemistry, um, they didn't really stress that as much as they did with other things. They really, really stress that now because that's one of the things that once I understood that, it made a lot of sense. And so redox reactions are extremely important when it comes to organic chemistry because you got to convert those functional groups. And once you convert those functional groups, you can make some really nice things out of that. So that's why they are so important. So what can you do? So let's just say you're synthesizing 2,4-dimethylhexadrenal 4-carbon alcohol. So you got to begin with a retrosynthetic analysis. Form the ketone by oxidation of a 2 degrees alcohol, made a 2-degree alcohol by Grignard addition to an aldehyde. Both of those compounds have 4 carbon and each must be synthesized from an alcohol. And so that's what they're doing there. Now you can begin with that. And then what you got to do is actually make both compounds needed for the Grignard reaction. Now, to complete it, the synthesis with the Grignard, you got to do the oxidation of the alcohol to the ketone. So with this is so important that you have to really look at how you accomplish this. Um, so let me just say with looking at this, um, and when we get into the chapters with carbonyl and everything in there, those chapters are so important because carbonyl chemistry, just looking at which carbon to attack, what to oxidize, what to reduce. This synthesis is very important. And so you're going to hear a little bit more about the Grignard reaction in the upcoming chapters and everything. I am going to stop here. Let me see. I'm going to start on, and I want to look at chapter 18 real quick. So hold on just a second. I'm going to pull it up just to take a look at a few things. pretty long too. Hold on just a second. I'm gonna just share this real quick. So with that, um, we're gonna get into talking about aldehydes and ketones. We have pretty much started talking about them, but what this chapter is going to be all about is aldehydes and ketones, and talking about the carbonyl group. And like I said, we're going to talk about this, and we're going to get into everything. But that's really what we're going to talk about, and we're going to pick all of this up, like I said, um, on Monday. Um, so, what I want you guys to do is go back, read back over chapter 17. Make sure that you understand chapter 17. Start working on the homework associated with that, because I think I have assigned that homework. And really just dig into that, because when we get into chapter 18, um, pretty much next week, that's what we're going to be looking at is just going into what do aldehydes, what do ketones do. We touched on it some in chapter 17. Like I said, chapter 17 was just basically giving you a preview of the last part of everything. But we're going to really dig into aldehydes, ketones, and then the amines. Those are the last few groups that come into this that I really wanted to go over and touch on all of the major functional groups. So one of the things that I wanted to do is make sure I touch on all of the functional groups first, and then we can get into other things. But understanding carbonyl chemistry is also very important. So I'm going to stop here for today. On Monday and Wednesday, we're going to do chapters 18. And like I said, I'm going to try to carve out some time and record the other groups. But the last test that you guys are going to have for the class would be on chapter 17, 18, and I think it's 23 that's dealing with the amine groups. So that would be the last test that you guys are going to do. Um, as far as other homework, you will have homework on those other chapters, so that because that would be on the test on your final. But I'm not going to give you a comprehensive test on it. I may give you some quiz questions and stuff on that, but it won't be a full formal exam on it for that. But you will have questions on that that I'll put into a quiz for you guys. And so I will do that. I will also just real quick. I'm gonna look at something. Um, Trying to see. All the meditation, synthetic sequence. I may need to hit on polymers. Um, I know what you guys are wondering what I'm doing. I am looking at what um, questions that need to be on your final exam and what topics those questions cover. And so I'm just looking at trying to make sure, is there anything else that I need to hit on? All right. All right. So what I'm gonna do is I'm looking at this, and what I am gonna try to do, you guys, other than looking at your organic chemistry book, is actually try to make some type of study guide so that you can have and see what is actually some things that you need to look at from the book that could be covered on the exam. And like I said, what other chapters that we don't get to, what I would do is make sure that I cover those in some videos that I will post on my YouTube channel. I think that's all I have for today. Um, if you got any questions or anything, reach out to me, send me emails. And I know a few people had sent me some questions about other things um, and everything. So make sure you reach out. I'll try to get back to you as soon as I can. Usually I have my phone on me, so I do try to reply via email as quick as I can. Um, so that's all I have for today. Um, I will see you guys on Monday. So go ahead, start looking over your homework, start studying, looking at this, because some of this will definitely, that's why I said I pulled out my sheet, that some of this will definitely be on your final exam. And like I said, I'll make sure that I make the videos of other things that will be on there and I will post them. Okay, guys, have a good one. I'll talk to you guys later.